Hi folks, welcome to the one more last video on solid principles. We have gone through quite a huge journey in terms of discussing what are solid principles. I think we have almost gone through around 10 videos. Now we were discussing what are solid principles, what the violations actually look like in each of those solid principles, and then we went through another 5 videos trying to understand how to refactor our code to make our code comply with the solid principles. We also saw when we were refactoring our code to achieve the compliance, how the complexity of the code keeps on increasing. The number of classes increase, the number of interfaces increase, the number of relationships that you have to establish between the classes and the interfaces keeps on increasing. I'm pretty sure after having gone through the whole exercise, you might be actually starting to question the whole logic behind the solid principle, and is it really worth trying to make your code so much complex? I mean, take each one of these principles, say single responsibility principle. What is responsibility? I mean, why do you reduce it to one single number, single responsibility? Why can't it be similar responsibility? Then comes the open and closed principle, which talks about keeping your code more flexible for the future extensions. But once again, the question is it really possible to think of all the possible future scenarios against which you will have to guard against your code, ensuring that it is possible to really extend it like that? Then comes the Liskov substitution principle, which talks about substitutability. How do you quantify substitutability? It's just like saying pay more attention while you are creating inheritance structure within your classes. Is that it, or is there more to it when it comes to substitutability? Then comes interface segregation principle, which basically tells you to create very custom specific interfaces to suit your requirement. That also means there will be an explosion of interfaces and the classes that are going to implement those interfaces. Is it really worth taking that much complexity into your code? And then last but not the least, which is dependency inversion principle, which basically says that there should be a abstract relationship between the higher and lower modules. But once again, is this too much abstraction not going to increase the cognitive complexity of your code? And after having gone through almost all these different principles, you might actually start wondering, are they really principles? I mean, can't we just call them as patterns or guidelines or thumb rules that you can follow given a particular context, and choose to still do what you want to do if something contrarian makes more sense? So we will try to spend some time trying to make sense all of these things and really scrutinize what we keep hearing about the solid principles. So before we get down to the business of critiquing solid principles, let's rewind a little bit back and start talking about something on which these things are basically based on, which is object oriented programming, or OOPS. Anybody who knows object oriented programming, you ask them what is OOP programming, they will tell you about three things, that is encapsulation, inheritance, and polymorphism. What is encapsulation? You basically ensure that your fields, that is data and methods, are combined together. They are like sitting in one single room, they are like roommates, completely aware of each other, and you are also in a way hiding it from any external interference. That is what encapsulation is. And then comes inheritance. This is a way like you are inheriting certain good traits from your parent. You might inherit bad traits as well, but let's not go there. Then comes the last, which is polymorphism. It is basically inheritance that makes the polymorphism possible in object oriented. It's in a way that a subclass can behave like a superclass by providing a very specialized implementation of the superclass behavior. If you recall, it's like basically dog is a animal, cat is a animal, so dog can be replaced with the animal, or it can behave like an animal wherever you can replace it with animal. That's what polymorphism is all about. Polymorphism is very main crux of the object-oriented programming languages. And all these are backbones of OOP, and it is on these OOP foundation the solid principles are actually laid on. Now, I don't want to once again bore you with all the definitions of all the principles. We have already done that in the last 10 videos. If you are watching this particular video, probably you already know what are those principles, what they mean, what are the violations look like, and what are the adherence look like. Now, we will go beyond that and we will try to dissect these principles to their bare minimum core and try to understand what are they trying to bring in to the table of writing better quality code. If you go back to the dictionary definition of principle, because we are calling it as solid principles, right? What is the dictionary definition of the principle? If you go and search in the dictionary, principle basically means a fundamental truth or a proposition that serves as a foundation for a system, or it's like a chain of a reasoning. Is solid principles a principle in that real sense? Is it a fundamental truth, something like Earth's gravity? Or depending upon the context, it can actually change. So let's dig in and see each of these principles at their bare minimum. Let's start with the first one, which is SRP, that is single responsibility principle. It's in a way saying don't put all your eggs in a basket, or in other sense, don't make a Swiss knife out of your class. Your class should be custom built for doing one thing and one thing only. Don't try to make too many things in one single class. That is what single responsibility is all about. It basically comes from the concept of cohesion and coupling, a very commonly used term in software engineering. You might have heard this term, something like your software should be written with loose coupling and tight cohesion. Coupling is very easy and tangible thing. If you write a bad code, then it forces you to change a lot of things at different places. That is a very badly coupled code. So that is very easy to understand. But cohesion is a little bit fuzzy concept. It is very difficult to quantify. How do you say that a particular class or a module is cohesive? A guy called Grad Booth basically says that a class should not have more than 3 to 5 responsibilities. So in a way, it need not be one single responsibility. It can be a bunched together responsibility. Now, the question is, what do you mean by bunched together? In another way, you are basically saying that these are very similar responsibilities. So instead of saying it is a single responsibility, you can also say that it is similar responsibility. So if it has to change, it will change for similar reasons. It is not really, strictly speaking, single reason. So what it is really trying to say is, when you are creating classes, try to get together things which are going to change for very similar reason and separate out things which change for different reasons. So wouldn't it be better to call them as similar responsibility principle? Maybe yes, maybe no, but the solid single responsibility principle name has got stuck and people seem to like it. So we will continue with it. But single responsibility doesn't really mean single. It is similar, cohesive. That's what it really means. So SRP is more of a very general software engineering concept. It is not something very much related to OOP. It is a kind of a synthesis of that guideline for OOP. Then comes the next principle, which is open and close principle, which basically says that your code has to be ready for changes for future. You don't have to basically break your existing functionality to add a new functionality in your application. It is once again talking about code management or management of your application or software. You want to make sure that your application is easily maintainable and manageable for long-term extension and modification. It's more of a general software engineering concept. But if you look at it, the OCP might not be a really principle at all. OCP suggests that your application should be open for extension but closed for modification. But however, this is very challenging to achieve when you want to practice it while you are developing your application. Prematurely closing your classes for modification can really play a havoc for building your application. If you really own the code and you are not dependent on any other code, you have a method and you have a class and you have a complete control over who is going to use that particular class and how you are going to use that particular class, then it is perfectly fine to make your code open for modification, because ultimately you are owner of that particular code and you can go and modify that particular code as per your will and wish. The problem really starts happening when you have code or you have interfaces, you have APIs which are published APIs or published interfaces, which once you publish, people are dependent on those. In that situations, you can't really go and start changing things, because if you start changing things, it will start breaking things for others. So this open and closed principle is mainly applicable to published interfaces. But for a closed system where you are complete owner of the application and you are going to basically maintain the application, then prematurely closing your code for future modification or trying to write your code with such a level of abstraction so that you can extend it without modification can bring in a lot of unnecessary complexity in your code when actually it is not needed. So once again, you have to be really careful about how you want to apply OCP in your code. So of course, follow OCP, but if you are writing an application which is completely owned by you, you can relax a little bit. But if you are writing application which is going to be interacting with other systems which are not going to be written by you, which are like published interfaces, then you have to really pay extra attention to the open and close principle. LSP basically says that the object of the superclass must be substitutable with the object of the subclass. So in a way, what it is trying to say is, if you have a parent class, the child class should be able to come and behave as if it is a parent class without creating any chaos. Most of the times people think that LSP is just about polymorphism and just inheritance, but that's not what it is just about. Polymorphism allows objects of different subtypes to behave like a common supertype without breaking the existing understood contract. So the main concept here is, when the subtype start behaving like supertype, they should not change the contract. They should not change the behavior. If they start changing the behavior, then it is a violation of LSP. So we cannot think substitutability only purely in terms of polymorphism and inheritance. We have to think it in terms of testability. You might have heard of this very common example where you have a class called bird and then you have a sparrow which can fly, but penguin can it extend fly functionality. So that is one of the classic example, but that doesn't really capture the real concept behind LSP. Let's take a very much more realistic example. Let's assume that you have a functionality which is about something like list or most recently used list. It is a list which can not have, say, duplicate entries, and it cannot have, say, even null entries, and the most recently accessed item comes and sits on the top, and if you have already visited some entry and it's somewhere in the middle, and if you visit it again, it comes and sits on the top, and there can be only one entry. So this is a kind of a list that we are talking about, but which is like a behaving like a stack with most recently accessed element on the top of the list. Now if you start thinking that this is a kind of a list, and this most recently used list starts extending list class, then initially it might not become very apparent that this is violating LSP, because in list duplicates are allowed, and any such functionality in the list which perfectly passes all the unit test cases will start breaking in the most recently used list functionality. So even though it looks like this list is substitutable with a commonly used list, it is really not. So we have to pay attention about two things when we are talking about substitutability. That is, of course, it inherits and it is polymorphic in behavior. But more important than that, we are also talking about the test cases should not be breaking in the subtypes. Now let's talk about the next principle, which is interface segregation principle. This is like saying don't overstuff your menu with too many things. Don't create a very massive interface and end up with a situation where a lot of subclasses that implement that particular interface don't really need some of those functions from that particular interface. But this also means you end up creating a lot of interfaces. If you pay more attention to it, what it is actually a single responsibility principle that is being applied to interfaces. So in a way, you are getting a SRP for interfaces in the interface segregation principle. You see, interface segregation principle basically comes from the role decoupling or normalization that we might have seen in the databases. You might have heard these things like one normal form, two normal form, three normal form. What exactly are you doing here? You are basically trying to break the tables into much more smaller tables so that each table is very specific to a particular requirement. In the same way, you are basically trying to break the interfaces such that the more cohesive functionalities are together in a single interface, and the ones which don't make sense, you move them to a separate interface. But when you are trying to do this, a balance need to be stuck. Otherwise, there will be a huge explosion of interfaces. You will end up with too many interfaces that you might actually may not use at all. So you need to be little bit careful and strike a balance when you are segregating it into much smaller interfaces. So don't go overboard with this concept. Once again, try to put cohesive functionalities in the same interface so that you don't end up with too many single function interfaces, which is once again very much similar to a single responsibility principle, which we were trying to say that it is actually meaning similar responsibility principle. And finally, last but not the least, is DIP, that is dependency inversion principle. There is a catch here. Most of people actually confuse dependency inversion principle with dependency injection. They are two different things. I mean, they are in a way helping one another, but they are not really one another same. Dependency injection is really a very fancy way of passing the arguments so that you can reduce the coupling between the modules. That is what dependency injection is, but that is not the essence of dependency inversion principle. Dependency inversion principle is much more than that. It basically says that the higher and lower modules should be dependent on each other through abstractions. This basically allows your code to be kept in a flexible way. And if you think about it, dependency inversion principle is actually a marriage between single responsibility principle and Liskov substitution principle. It basically ensures that your code is loosely coupled and not only that, easily substitutable. And how do you do that? By making sure that these two higher and lower level modules are dependent on abstractions. And this is what allows your code to become very modular. So there you have it. This is what basically solid principle is all about. The name solid principle sounds very impressive and comprehensive, but at the end of the day, these are just once again common sense software design principles, probably which might have been there earlier as well, but have now been crystallized and consolidated together in such a way that it becomes very easy to follow. But once again, when you are applying these principles, don't go overboard. Always look for what really makes more sense to you. One of the very most commonly heard quote as far as solid principles is, don't apply solid principles in a dogmatic way as if you are trying to satisfy some kind of a rule or a higher order or higher god to say that my code is now compliant with solid, so now it is a good code. That's not the case. So don't apply solid principles in a dogmatic way, apply them in a pragmatic way. And I think that is probably the most least dispassionate way of saying how to apply solid principles in your code. So apply them, but not in a way where it becomes a monster. So what is the key takeaway? Keep your code simple, flexible, so that it can be easy to change later. That's what it is at the core of it. So always keep that picture in your mind. So I hope you like this. Do let me know about what do you think about this topic. Thanks for your time.
That brings us to the end of this particular video. Don't forget to like, comment, share the video and subscribe to the channel. Take care. Bye.